All right, I'm gonna go through the Chapter 9 test, 9 and 10 test review, and talk about the problems, the solutions, and kind of the thoughts I'm having as I'm reviewing. Now, remember that the Chapter 9 and 10 test is our proportions and means. Come on. So it could be one prop Z test interval, two prop Z test and interval, one sample test T test for means, one sample T interval, and then the two sample T procedures for means, and then the paired T test. We're gonna make sure we're on top of that as well. So looking at question number one, we have a two-sided alternative. That's the first thing that jumps out at me when I'm looking at this problem. A z-score of 0.8. So the p-value of this, if we're thinking about the picture, under the z, the normal curve, we got 0.8 as the value, which would be that or something more extreme. But because it's two-sided, kind of the cheeky bit to this question is that I also have to consider negative 0.8 and everything less than that. So you can look this up in your z table and just find less than negative 0.8, which is 0.2119. And then if you double that, because it's two-sided, you're going to get the answer C, 4238. Number two, an opinion poll and 100 college students. N is there. N wasn't useful in the previous problem because it was a proportions problem. In all, 53, so this would be X, right? The number of successes. If the proportion, let's say, is good, what is the hypothesis? Does the poll give convincing evidence to conclude that more than half? So that's going to be our alternative, is more than half that are good, where the null is that it is half. Technically, it could be less than or equal to under the null, but we're going to say it's equal under the null, which means it could be any of those guys, and then the less than, or excuse me, greater than alternative there leads us to an answer for A in number two. For number three, again, a two-sided alternative that jumps out, a sample of size 10, because we're talking means here. This could be, if that's n, we're talking about degrees of freedom equal to 9. Let's see, sample mean of 103, we have a p-value of 0.08. Which of the following is true at the 5% significance level? Well, because the p-value is not low enough, we cannot reject the null, and conclude the alternative. So we lack the evidence to conclude the alternative. There is insufficient evidence to conclude the alternative D is the best answer there. Which of the following is not a required condition for performing the t-test about an unknown population mean? So the t-test, remember that the t is x bar minus mu over s divided by the square root of n. So random, that is one of the conditions. The population standard deviation sigma is known. That's not needed. We don't need that because it's the t procedure, and the t procedure relies on s. That's why we talk about degrees of freedom. Just to run through the rest of them, it does need to be normal, or the central limit theorem kicks in, and then independence would be the other condition that needs to be met. So B would be the best answer, as which one is not required. An appropriate 95% confidence interval for mu has been calculated as this guy here, based on 15 observations. from a normal population. All that's good. We want to test the hypothesis that mu is 0. I probably could have guessed that based on this interval. Which of the following is a legitimate conclusion? Now, 0, the null, falls in the interval. Therefore, it is one of the plausible values that could be the answer to whatever the context of this problem is. So, since it does not fall outside, this is kind of like the previous problem, I guess problem 3 there, we lack the evidence against it here in number 5. So this is a fail to reject situation, and specifically it's failed to reject at the 5% level, because a 95% confidence interval is going to have 5% in the tails, and because it was a two-sided test here, we would reject anything that's far enough in the tails. So a 95% confidence interval is analogous to the 5% alpha level. Number 6, which of the following increases the power of a test? So to increase the power, let's see, things we know about power is it's equal to 1 minus beta, which is the type 2 error. So as type 2 decreases, that'll increase our power. And then visually, if we're convinced that we're going to reject anything greater than some value, let's just say this is where we're going to reject over there, you have to be told something else is true. And so if this other distribution is true, things that would increase the power, if you remember that power is the probability of correctly rejecting the null. So not only do you reject, but you do it correctly when this other distribution is true. And so that power, as I move this, right, as the new information is farther and farther away from the old information, the likelihood that I reject is going to increase. You should be looking at the area under this curve to the right of my critical value here. So moving it farther away, for example. Increasing n is also another way to increase the power, because that's going to make these distributions, if the first one is here, and then the second one is here, now the distributions themselves, while not changing anything else, there's less overlap, they are more distinct, and therefore you are going to correctly reject a false hypothesis if n is large, if you have a lot of information. So all of those things go into it. Lastly, you could just make it easier to reject. If I move this rejection, let's see if I can grab it there. It doesn't look like it. If I were to move that to the left, if I move this way, and now I start rejecting everything over here, that's also going to increase my power. So let's run through these. Using a two-tailed test instead of a one-tailed test is not, that's going to decrease your power, because now you have to reject not only on the one side but on the other, and that comes at the cost of rejecting in the direction that you want. So let's see, that's no good. We said increasing your sample size would work. Finding a way to increase the population standard deviation, well, you can't do that. And second of all, you would want to decrease it if possible. Increasing the significance level, well, that was one of the last things we talked about as far as moving the rejection region and making it bigger. So that's looking good. And then perform the test many times, that's not going to help you at all. So increase alpha is the one in this case that works. Other things would be move the alternative farther away, or increase n. Those are pretty much things you can do. Cruising down to number 7. Let's see, where average survival times is 2 years early in the trials. 5 subjects, let's see, find that they have an average survival time of 4 years after the diagnosis. The survival time is double. The results of a t-test for the mean survival time are not statistically significant, even at the 0.1 significance level. Which of the following is the best course of action for the researcher? So even though on average it was 2, there was this 5 subject set where they had an average of 4 years, which sounds good. But when they ran the test, it turned out it wasn't significantly more. Now, what could you try? Should you just give up? Just abandon the study? I guess maybe, but let's see if we've got at least maybe something we can try. Is it more likely that there was just an arithmetic error? While that happens to the best of us, let's see if there's something she can do, assuming that the calculations are correct. Increase the significance level of her test so that she rejects the null hypothesis, since the treatment clearly has a positive impact. While that would become significant, we know that that's going to come at the cost. You're going to then make a type 1 error more often, so isn't necessarily the best move. And as far as significance levels we've talked about, 0.1 is at pretty much as big as we're willing to go. Use a z instead of a t. There's no need for that. This is a means t-test. Of course it is. So don't use z. Let's see. Expand the program to more subjects. Well, we always like to say that as we increase n, we get more specific. Things tend to get better if we can increase our sample size. 5 was pretty small. In our t calculation, x bar minus mu over s divided by the square root of n. If that's only 5, that would probably be the best strategy here. As far as a best answer, E. Number 8, we have a planner comparing traffic patterns for 2 different intersections. Randomly selects 12 times between 6 and 10. So one random selection here, 12 times. And then looks at each of the 2 intersections for 10 minutes. Plans to test the hypothesis that the mean difference in the number of cars passing through the 2 intersections during those 12 times is 0. Which of the following is the appropriate test? So we're talking about time. Probably a means, average time, mean difference. Here we go. So let's get rid of our z's. We don't want z tests, and we really don't want proportions. So I'm going to get rid of proportions as well. This really comes down to, is it a 2-sample t-test or is it matched pairs? And I think the biggest indicator is the one random selection of 12 times. So you've got, for example, time 1, time 2, time 3, time 4, and then you've got intersection 1 and intersection 2, and you're going to have a measurement there, a measurement there, a measurement there, a measurement there. So these 2 measurements for intersection 1 and intersection 2, they're paired up at this time. That's the categorical variable that's connecting these 2. It wasn't a random sample of times at this one intersection and a separate random sample of times at this other intersection. It was only one random sample, so that leads me to think it's going to be a 1-sample T procedure. In this case, the matched pairs, where we're looking at the difference, is our 1 sample. Number 9, we've got a 2-way table here, and the descriptive statistics, means, and standard deviations. Ultimately, we want a 95% confidence interval. And so when I see 95% confidence interval, a lot of times I'm thinking to myself, okay, that's 1.96. But remember, since we're talking means, 1.96 was the z-score. And that's not what we want. We want the t for the appropriate degrees of freedom in this problem, because we're talking means. This is mean tooth damage. So t with degrees of freedom equal to the more conservative n minus 1 in this case. So we're going to go with 9 degrees of freedom. in this case, the more conservative of the two. So if we go look up in our table the t for 95% confidence, which I'll get rid of that, I don't want that, and 95% confidence, 9 degrees of freedom on the t table, the number I come up with is 2.262. So I got to get rid of these. They're no good. Now, of course, if you were to calculate this on your calculator, you would get the calculator's calculation of degrees of freedom, I guess, for lack of a better thing to say there. And we don't, while you can use that for an inference procedure, if you're kind of otherwise left without that, you're going to have to look it up in the table to get the appropriate degrees of freedom. So that's 2.262. Now the rest of the problem, now that we've narrowed it down to these two options here, is how do I put the standard error together? That doesn't seem to be the right t-value. And remember that it's the square root of s squared over n1 plus s squared 2 over n2. And you have your standard deviations. These are your s's. We have to square them. So that's b, where that happens. The mistake that gets made, and this gets made often, is people will choose a because they see s over n, which for the one sample t was s over the square root of n. But in this case, we have to write it as the square root of s squared over n because we added the two variables together. And remember, we can't add standard deviations. We can only add the variances and then take the square root. Let's see, coming down for 10 through 12 here, we have this situation. We have these contests to determine who had more rainy days, because that's important. And let's see, we have a test, two-sided difference here, 5% significance level. Randomly select 60 days for the past 5 years. Janice found that measure rainfall on 17 of the 60, so that's her success rate, and then 12 out of 60 for the other group. So it really is 17 out of 60 distinctly different or significantly different than 12 out of 60. That's what this is testing. And it's just that it's different, right? We have a two-sided test. They did not test, is it rainier in one particular direction. So the first question, number 10, Janice and Linda's test statistic is 1.07. Which of the following is the closest appropriate p-value for the test? You can go look this up. The area to the right of 1.07 in the z table, 0.1423. Again, it's a two-sided test, so we're going to have to double that, because as different would be negative 1.07, which is going to have the same area. Number 11, which of the following best describes what it would mean if Janice and Linda's test resulted in a type 1 error? And type 1 error is when you reject the null, but the null was true. That's the type 1 error. So they say that there's a difference. They conclude the alternative when in fact there was no difference. And among them conclude that there is a difference when in fact there wasn't. That happens to be A. So reject the null, conclude the alternative, but in fact the null was true. And then for number 12 here, the test statistic, what would be the standard deviation for this? And it's a difference of proportions test. So it's the p hat c q hat c over n1 plus p hat c q hat c over n2. Remember that in the two-prop z test, which is what this is, you have to pool, and p hat c equals x1 plus x2 over n1 plus n2. which, let's see, we had, I think, 17 and 12 successes. 17 and 12 over 60 plus 60. And if we knock that out real quick, 17, we get 24% as p hat sub c. So let's see, that looks like this guy here, right? 24, and then 76 would be q hat c, and the ends are the same. This is not good. That's for means. This is nothing we've ever seen before. This would be if you made the mistake of not pooling, perhaps, where you use the p hat 1, p hat q hat 1, and then p hat 2, q hat 2 there. That would be that mistake. And you never want to add the standard deviations, so we wouldn't do that one either. So I'll pause here and make a separate cast for my solutions to the free response questions that you can check out after you've given them a shot.